So, ladies and gentlemen, it's my pleasure to start another webinar organized by ISPRS. It's exactly 2 p.m. of Central European Summertime, and I would like to welcome another expert in our group, ISPRS group, and it's Batu Han. I know him like Batu Osmanoglu, and he's a research physical scientist at NASA Goddard Space Flight Center. He holds a PhD in synthetic aperture radar, SAR, interferometry, and he has been a part of Istanbul Technical University, later on University of Miami, University of Alaska at Fairbanks. And he has worked on applications for observing surface deformation, measuring target velocities, and radar design. He is the principal investigator for the airborne SAR instrument, and he serves as one of the NISA, this is NASA ISRO-SAR mission, deputy application leads, candidate architecture deputy lead for surface deformation and change mission study, and one of the disasters program coordinator at the Goddard Space Flight Center. This is his profession, and now his relation to the ISPRS. He's a chair of the Working Group 2 of the Technical Commission 3 dedicated to remote sensing. And his topic is microwave remote sensing, and the title of the session is Golden Age of SAR. So please tell us more after the question mark. Thank you, Batu.
Thank you so much, Lena. So, of course, yeah, my name is Batuhan, but it's often too long for many people. So I learned to go with just the first 4 letters to make it simpler. Yes, today I would like to tell you a little bit about what we are doing in terms of synthetic aperture radar and where we see we are now and where we think we might be going in the future. And I'll sort of try to make the case and ask the question to you if you think we are in the golden age of SAR, or if you think this is just a regular day in the office. So here's a brief outline of what I would like to tell you today. So we will first start with the why we use SAR. This is sort of like the why we care, why does it matter why does it matter if you're in the golden age of SAR, or if it doesn't exist at all. And then I would like to tell you a little bit about how we came here today, essentially, with all these different missions, and where they came about. And also I would like to talk a little bit about the current and upcoming systems and their distinguished features compared to the previous sensors. And we'll also talk a little bit about future and where we think the future may go. What you see on the right hand side is essentially an eye candy, but it is another look of radar data. What you're seeing is the similarity coherence metric of interferometric SAR data processed globally using the Sentinel-1 data by a company called Earthquake Data in the US for these NISAR and surface deformation change mission studies that we are working on. This basically tells you when it's bright over 12 days, you see that the signal is highly coherent. You can work with that signal to get deformation estimates really well. And also in a sense, it's a change matrix, like how the globe changed, how the surface changed over 12 days in the fall season. And you could go to the link at the bottom and essentially find all the different seasons and different time scales and see how different land covers actually change. So this is already one of the big applications of SAR. It's in a sense change detection. But of course, there are other applications that synthetic aperture radar data helps us with. So one of those things are often on top of our heads these days about the climate risk and the global food security. How do we ensure that we are actually providing enough food for the growing population of the world? Another critical resource that we have, worldwide is fresh water. So with SAR being very sensitive to the water, we can actually map fresh water really well. And of course, there's other areas of change. But one thing that I would like to highlight is the disasters management and hazard response. With its ability to image day and night consistently through clouds, synthetic aperture radar images are often the first imagery that we could get when a disaster happens. And this, of course, wouldn't happen if we didn't have all these SAR satellites, and we'll talk a little bit more about that in the upcoming slides. But if we talk about the applications in a visual sense, these are sort of just some examples of what type of things you can do with synthetic aperture radar data. So, you can look at deformation on the top left. That's essentially a picture of an earthquake, which I always find quite surrealistic, that like you can picture an earthquake and see how the world deformed. In this case, you're seeing the Ridgecrest earthquake, where two ruptures actually happened between these interferometric pairs. And then you could take a look at the same data, but this time map damage, where we see damage on the surface that could mean, building collapses or also surface ruptures. You could look at the surface flows like landslides or lahars or volcanic flows, which is the cyan to purple colored image, the third image from the top row. And then on the right-hand side, you have the disturbance, change detection, often indicated by farmlands are very good examples of that. So you could really see when the crops are actually put in the ground and when they're harvested. And also you could track their development in a sense. And right below that, you actually see a study about rice paddies and how different crop types could be identified. And rice is a very good one. So it doesn't, SAR, works really well for some crops, but not all. But rice is definitely a good case. If you walk towards left, then you see this green colored image over the gray background, and that is the biomass image from our Indian colleagues from ISRO, where we can use the radar backscatter data to actually estimate how many tons per hectare biomass exists on a given plot of land. And then to the leftmost on the bottom row, you have the ice sheet velocity and sea ice deformations. So these are all amplitude tracking applications where we can actually see how these glaciers are moving, which have turned out to be a lot more dynamic than we initially thought, several years ago, right? So or initially people were thinking, yeah, you could, map these glaciers once a decade and it would be the same, but now we're realizing that they're actually much more dynamic than otherwise. If we, look at some of these examples in a bit more detail, here's an example from our colleagues at JPL, where they processed more than 800 interferograms over a long time series. And they can actually map the breathing, let's say, of the ground as the Los Angeles Basin aquifer gets, supplies water to Los Angeles and also gets refilled over the seasons. In a sense, the point of this slide is that right now we're in the era of interferometric time series. You could also say that it is a SAR time series, looking at the very first slide that I showed you, where, we can analyze the coherence change over long time periods. With this type of data, we could look at the lags and how different parts of the ground are reacting to different geologies. So, faults are obviously well-known barriers for the aquifers, which are drawn on the left-hand side map. And also on the right-hand side, you can see the phasing of this signal, the recharge. If you say, uplift is due to recharge, you can basically see when is the recharge happening most, and therefore you could get a sense of how healthy the aquifer is. And of course, there are many studies since water is such a precious resource, especially in areas like Los Angeles. Another study that we have done looking at water is, with our colleagues at University of Alaska Fairbanks and the sport group at Marshall. We have realized a hydro-SAR service, which basically looks at Sentinel-1 data routinely over a large swath of land in Southeast Asia, where we get these RGB colored images. And then we can also extract the water surface areas. And these surface water maps are actually quite helpful in terms of managing the monsoon rains and knowing if a certain area has more than fair share of rain, causing potential flooding and issues to the people in the area. And in remote areas, this is quite important. Another thing that we have recently done was the earthquake in Izmir, Turkey, where we worked with our colleagues in JPL at ARIA to do a damage proxy map. And you can see in this animation where we focus on several buildings where the damage proxy map is showing disaster where we or damage, where we are able to confirm those with the high resolution optical imagery from WorldView GeoEye satellites. So if you think about it, of course, what synthetic aperture radar sees is very different than the optical sensors. In a sense, the optical sensors provide you a collapsed building versus a standing building type of verification, while the synthetic aperture radar can actually highlight change if that building moved significantly, as small as a few centimeters. We would be able to pick that up and map. So that has been also quite helpful in areas around the world to map damage. And one thing that that we looked at also at the beginning of COVID was how these how this disease is impacting the ports around the world. There was a report of slowdown at the Chinese port, so we decided to look at that. And basically, what we're able to see, and hopefully you'll be able to see in the next few seconds of this video, is that we see a lot more ships in yellow offshore, essentially waiting to go into the ports. Of course, we didn't quite know where the ports are, so we said, let's count the ships that are close to the shoreline as a port, and let's count the number of ships that are outside the port, and do a map of that. And you will see that around this day of February to March, you start seeing the rapid increase, and that essentially was caused by this COVID, and created a lot of disruption in the shipping industry. And a final example that I wanted to show you about, why we care about SAR is from the St. Vincent volcano. So since the Christmas, 2020 Christmas, there was signs of a potential eruption, and the disasters group at NASA started paying attention to this. And with our colleagues at JAXA, we basically asked them to continue monitoring this volcano. On April, it essentially erupted. And what you're seeing in these pictures is on the left-hand side, you see before eruption and after eruption. The red color indicates which way the volcanic flows went, and that sort of provides information to the first responders where the people at risk are. And of course, if another eruption happens, how the topography has changed and where the next flow might go. And in the grayscale images on the right-hand side, what you see is the dome growth. So this is before the eruption, starting around January 15th. In the red circle, you can sort of see this dome forming. and then of course it eventually explodes in April. So this was done by our team at Goddard. So then here's the question, right? Are we at the golden age of SAR? Is this sort of the peak of the synthetic aperture radar data? Or are we in some sort of a renaissance, maybe, you know, where we have already seen these techniques demonstrated, and now we are refining them, and in a sense doing them a lot more often? Or is this just another day in the office in terms of progress towards a continued sustained SAR mission? So here's a few looks at you know, where we came from. So what I'm trying to show you in this slide is essentially taking a look at the frequency diversity of different satellites that we have in space. When we talk about synthetic aperture radar, just like the colors in an optical band, the SARs have bands, and different bands are sensitive to different things on the ground. So at L band, for example, you're a lot more sensitive to the ground, where you could penetrate some of the vegetation, while at C and X band, you're more sensitive to the changes in vegetation, and you see those signals much more dominantly. So we started around 1978 with CSAD, which was the first civilian SAR system. It lasted about 3 months, and then there were several shuttle missions, which were short in duration. That's why the bars are almost invisible in this chart. But one of the shuttle missions that I would like to highlight is SAR-C, which actually had a three band observation capability. It could observe at L, C, or X bands. And it also was a quad polarimetric SAR system. So that is quite a unique capability that we still haven't necessarily been able to match with any other satellite systems that we have. Of course, around 1990s, we started getting these consistent imagery collections with the European systems, and the JERS is, of course, from Japan, and the Canadian RadarSat missions. They, with the exception of JERS, the early days of SAR has been single frequency, in a sense, like single color, if you wanted to keep that analogy of optical imagery. Just like, you know, you only get the red band, but not the red, green, and blue to form the image. So, but later on, we started getting more images, more data collections at different bands at L and X, and especially nowadays, there's a lot of X-band data available. One other thing that I wanted to highlight is the SRTM, and it was the last shuttle-based radar mission for civilian applications. And that provided the DEM, which was a major application until, you know, nowadays, of course, we're all migrating towards the Copernicus DEM provided by the, you know, Europe and DLR's, you know, TerraSAR-X and TandemX data sets, which are amazing in terms of quality and what we can do. Here's another plot of where we are. So if this time I am trying to look at the resolution, and for resolution, I'm mostly looking at the range resolution, which is directly proportional to the bandwidth of the instrument. The larger the bandwidth, the higher the resolution that we see. Again, the different colors indicate different bands of operation for these SAR systems. So you could think of them as, you know, again, different red, green, and blue analogies to optical imagery. But if you take a look at it, you sort of see that you know, we have been making progress towards higher resolution systems. You know, towards the right-hand side of the figure, you see that there's no more low-resolution systems anymore. But you also see that the dashed lines indicate the ITU band allocations for Earth observing systems. So essentially, you know, the pulsar's maximum bandwidth is right on the maximum bandwidth that the ITU allows us to do. Similarly, Umbra, the X-band commercial satellite, they have received authorization to transmit up to 1.2 gigahertz or 1200 megahertz of bandwidth, and that is also at the maximum limitation of the X-band allocation. So we are doing much better in terms of resolution. What we probably need is just a bit more consistent collection at the highest resolution. So far, we are often, not using these systems at their highest resolution all the time. Similarly, if you look at how much imagery, how much data these satellites can collect, this is a look at the orbital duty cycle, another way of saying how many minutes per orbit these satellites can collect data. So over here, what you see is that it seems like, we always had the capability of collecting imagery around 10% of the orbital cycle. And then towards the later periods, we see an increasing trend with systems like Envisat and Sentinel-1 especially. And of course, their dominance also comes from the wide swath compared to Envisat versus Sentinel-1, right? Sentinel-1's swath is much wider, providing a lot more coverage with the same duty cycle. I added NISAR to this slide, even though it is not up yet, but NISAR's duty cycle is at L-band is planned to be 50%, and with a swath of similar to Sentinel, around 240 kilometers. So in a sense, providing a lot more data. One other thing that I wanted to point out in this slide is that there is a new way of thinking the SAR business. Most of these commercial SAR companies are doing things very differently with much smaller orbital duty cycle, but increasing the number of satellites in the constellation. That's why you see, for example, ISI towards the bottom. So that, in a sense, changes the game a little bit for how we're collecting this data. Are we doing it with one satellite, or are we doing it as a constellation? All these things, the data that we collect essentially impact the resolution, coverage, and ultimately the file sizes of these data sets. In a recent study with our colleagues at Europe and Alaska, we looked at how the size of these data sets are changing and whether or not are they suitable for cloud processing or at home processing. Essentially what we're showing here on the right-hand side is how the data files, a single product has been growing since ERS2 and what is the expected NISAR data product. Of course, this goes back to how many bits you're putting on a given swath of land. So one metric of that is bits per meter squared. So if you look at that for Sentinel interferometric wide swath mode, that's on the order of about a bit per meter squared. If you look at the TerraSAR-X at strip map mode, again, this is not the highest resolution that TerraSAR-X can do. That's about 5 times higher. Of course, we know that the TerraSAR-X strip map is about 3 meters resolution, while the Sentinel-1 is, 4 by 20 meters resolution. Another aspect to think about that contributes to the product size growth is, of course, the area that these are covering, right? So for TerraSAR-X, we're talking about a 30 kilometers swath size, while with Sentinel-1, it's 240 kilometers. So those things do have a large impact in terms of the areas. So regarding data, one thing that I would like to ask the question is that, do we have a Landsat moment or have we already had it? Essentially, the Landsat moment that I'm referring to is the change in data policy where Landsat data became freely available after 2007. I'm showing 2 graphics on the right-hand side where this one is showing the number of publications that use Landsat data and Landsat time series, while this second one, this one is showing the number of data downloads from the USGS archives. So essentially, we see in that optical remote sensing community that there was great advantage of having these data freely available for scientific use. And we know that Sentinel is providing data in this manner, and upcoming Roselle and NISAR missions are likely going to follow suit as well, which is actually, I can say that for certain for NISAR. And some of these other data sets, like we know that JAXA is planning to open ALOS2's Pulsar 2 ScanSAR data as well. But as I mentioned in the previous slides, there's a growing capability in the commercial sector. So, and of course, there's many other satellites that we don't get the data freely available for scientific use. So the questions are, is there a way that we can actually get these data sets for science use available to the world scientists? And there are some already existing mechanisms, but they are still, in my mind, unable to create the Landsat effect that we have seen earlier. Okay, so let's take a look at these SAR systems, and let's take a look a little bit more about the future now. So here on the left-hand side, you're seeing the current status, and in the 2020 to 2030s, in the next decade, let's say, we have several missions coming up, like the Sentinel-1 continuity with CND. We'll hopefully have Roselle and also Tandem-L. NISAR is slated to go up. And of course, we're expecting many more commercial constellations. And ALOS-4 is also soon to go up as well. So if you look at these satellites and sort of only take out the ones that provide you open raw and SLC data access, you get a smaller set. And then if you look at the ones that can provide you global high area coverage, meaning lots of data so that you could look almost anywhere in the globe to do your analysis, then you get even less scenes. That is, I think, something that's we would be working on, and I'm hoping in the future we will start solving. For an assessment of the future capabilities, we recently looked at the upcoming satellites, upcoming missions, and their SWAT size and the constellation sizes. This was basically done purely to see how much data are we expecting to get. And for this, we looked at the space agencies and also the commercial satellites. But here's an eye candy again about what these satellites look like, the commercial, so the government space agency constellations. And I'll show you a couple of renditions of this type of animation where you see, where I hope you will see the differences. If you then, with this type of information, we could look at the archive. So in this case, we were looking at about 600,000 Cosmos SkyMed images and where they map on the world. We see that, there's of course a great density over Italy, Japan, and places like Western US, where we know there's active hazards, geological hazards. And on the bottom left, you can see sort of the density of these stacks, in a sense that in most places we're getting about an image every other month, and when we really get into the dense stacks, we're getting more than 3 images a month. So if you compare that with the Sentinel-1 interferometric wide swath mode, you see that, of course, Europe is much more acquired with the 6-day repeat. But you see a lot of data coming for most of the world, where it is often you can find an image more than a month, maybe every 3 weeks or so. And this was generated using 472,000 images. So we can then, take a look at these and try to make an assessment about what we expect in the future, which I'll get to in a second. But before that, I want to tell you a little bit more about also the commercial side. So we did a similar analysis based on what we think, what is the current status of the commercial companies, and what is their expected constellation sizes in the future. And then if you, in the grayed out numbers, you will see that there is some of these constellations that are, in high tens of satellites, right? 30 satellites or more. And so if all these realize, then it is easy to say that, you would be able to collect a local scale imagery at X-band almost every 10 minutes anywhere in the world, since all these commercial satellites have the repointing capability that they could really image fast. Here is another version of that same animation that I showed earlier. This time with the commercial satellites showing as the single cubes, and then we added the space agency-based SAR systems as well, which are also shown on the left. And there's also the future NASA mission beyond NISAR, which in the current working name is the Surface Deformation and Change Mission Study. So which we expect that will also have a lot of coverage, either through a single satellite or multiple satellites. Nonetheless, when we look at the future, to about 2027, we see that on the commercial side, we expect to see a lot of X-band coverage. So all these numbers in coverage are normalized by NISAR L-band. And on the upper right-hand side, you can sort of see the parameters for that, what that means to be, one NISAR size data collection. So if all of those commercial sector aspirations materialize, then we will get about 11 times NISAR coverage with that commercial sector. Of course, it is possible that there might be consolidations or some of these companies might not materialize, but we did not take that into consideration in this case. Then in the space agency side, if you look at that, then you see that there is not so much X-band data, but there is an increase in the L-band with the ROSE-L and Tandem-L, and we will have continued C-band access through the Sentinels and the RadarSat mission continuations. There is only a little bit of S-band data coming from NISAR. So in terms of frequency diversity on the space agency side, we're doing a little better than solely X-band, but we're mostly looking at the CNL bands. So the point of this slide is that essentially the commercial capability, if this materializes, is huge. But it's exclusively at X-band, and of course we don't know the costing, how it would be in the future. So it could be cost prohibitive for large-scale scientific analyses. But one thing, of course, that the commercial satellites have, which I'm showing here with a constellation in green and the NISAR in orange, is that there are many of them in space, right? Even if they don't have the individual collection capability as that NISAR has, because there are many of them, they provide the ability to image a given area much more quickly. And this is one advantage that we're trying to see how best to leverage in the future with the commercial capacity increasing. Okay, I would like to tell you a little bit more about NISAR now. We are, it has free and open data policy, and we're expecting it to launch in 2023. The launch date, if you have been following, it got changed due to some delays due to COVID. But it is planned to have a lifetime of about 3 to 5 years with onboard resources to last at least 10 years, depending on the orbit injection. But during that time frame, it will basically provide high resolution on the order of 10 meters or less, and cloud-free imagery twice every 12 days in almost all land surfaces. So here's a little bit more information about the instrument. It has this L-band and S-band, the dual band frequencies, and it will be the first dual band SAR system in space. And at L-band, it's using the sweep SAR technique, which I'll talk in the next slide more, but that provides it the capability to collect large-scale data sets. It is quad-pole capable, though most of the collections will be dual-pole. It has the ability to collect high-resolution imagery, most of the imagery will be on the order of 10 meters, around 20 megahertz for global acquisitions, which I'll also tell a little bit more later on. One thing to point out probably is that it is in a left-only pointing operation. This was done to not disrupt the time series analysis. As we said earlier, we are in the era of interferometric time series. The other point of doing that was that we could leverage the Sentinel-1 data for the Arctic. So this is actually the first time a NASA mission is using another mission to fulfill its observational needs. It will fly a 6 a.m., 6 p.m. orbit, as shown on the bottom right, and you can sort of see the schematic of the incidence angles and the altitude, the flight altitude on the right as well. So here is how the sweep SAR technique works. So if you look at the upper image, image on the right-hand side, there are 12 bins on the ground. And those 12 bins are indicated with different colors in the rows at the bottom, where you sort of see the orange and the green and blue. And essentially, the red is the transmit beam. So every so often, radar has to be quiet and do a transmit, and then it will listen. And obviously, when it's listening, we actually have multiple beams, as you can see, coming back to the satellite. So in a sense, it always has to keep track of multiple echoes coming back from the ground to enable this large swath operation. This makes the radar more complicated, and also this combination of data is done on board, so it is not reversible, which means that the data calibration and instrument calibration is really important to achieve optimum performance. If you look at the data that will be collected over the globe, over all land surfaces, this, NISAR will basically collect the same thing over and over again every 12 days with updates to the observation plan at regular intervals. What you see here in the different colors indicate different modes, where you see India as a different color because that's where the L and S joint operations will take place. The North America it's collected at high resolution, so that is also indicated in the dark green. And then there's also specific modes for sea ice and also ice sheets. So those indicate different colors, but overall it will provide about 1.6 petabytes of raw data per year. And it will also do, level 0 to level 2 data product generation. So in order to make sure that the data is used and it doesn't sit in an archive, we're engaging in an active applications program. And that is one of the things that I'm working on as the Deputy Program Applications Lead for NISAR, where we have several applications workshops, trainings, and engagement activities. And we recently kicked off an early adopters program and also instilled an envoys program where we ask key leaders in the field to talk to their communities about NISAR. Of course, there have been a focus on the disaster response community as well. And you can find more about these things in the NISAR utilization plan, which is shown on the right-hand side and available online. If you have an area of interest, I am fairly certain that there is a white paper that's written about it, if it is anything that can be done with NISAR. So there has been many science and applications white papers written for NISAR. They're all freely available on the website. And if you haven't had a chance to look at yet, I would strongly urge you to take a look. These are, easy to read 2-pagers that tell you a little bit about what NISAR is and can do for that. So one of the priorities that we look at in these communities is how the end users are planning to use the NISAR data in the future. Obviously, these are the needs. In a sense, these are the gaps in our observation currently. And since we're talking about the future of SAR missions, these things are the areas of focus for us. So one of the things that you see, for example, is that if you look at the top rows, top 3 rows, the ecosystems community, soil moisture and surface water extent are coming up as repeating themes, where we know that synthetic aperture radars can do these, especially the surface water extent, very well, but it is still seen as a need in terms of the community end user communities. Soil moisture is also doable, especially at L-band, and NISAR is going to try to address that, but it is difficult to get to at the moment. In terms of the geohazards communities, which are shown in this light red color, you see the displacement time series and damage maps are coming as recurrent themes and quite important. And some communities also indicate the need for low latency data. So that is also an area that I think we can grow in terms of our future constellations. And for this, of course, if we want to have that Landsat moment that I was talking about earlier, we really need to have a lot of users looking at the SAR data. Yes, the SAR data is different. It is difficult to interpret sometimes, and it is not as intuitive as the optical data. But nonetheless, with education and training, we can actually bridge the gap and allow people to use it to address their needs. For that, many of our science team members have done many trainings over the years. These used to be in person. So between 2018 and 2020, they have been to Nepal, Niger, Colombia, and Ecuador. But lately, they have been mostly virtual, which in a sense, had the potential benefit of getting more students into the virtual classrooms. One thing that I want to tell you before I conclude is the beyond NISAR, what we are thinking at NASA in terms of SAR observations. So surface deformation and change is the mission study name that we are working on, and this is essentially will be the guidelines for how we're going to realize the next SAR mission. So if you look at again, the areas of applications are on the left, which we have also spoken about them earlier. And on the right-hand side, you see the goals of this mission. If you look at it, one glaring difference is that we are talking about sub-weekly to daily rates in the very top bullet. That is not something that is often done easily. And especially when you consider the fact that we still would like to image the entire world in a reasonable repeat time. So that's a big change. And if you're also following up the costs of these SAR missions, the other thing is that the cost is much lower than what it has been for other SAR missions. So those were essentially coming from the National Academy of Sciences decadal survey. And then that didn't really include the imagery, the actual radiometric part of the observations. But NASA is essentially directing us to take a look at those architectures as well, so that we don't only get a geodetic signal, the motion of the land, but also the imagery. In conclusion, I think we are seeing a great capability increase with systems like Sentinel-1 and NISAR that are providing global scale high-resolution imagery with open data policies that is bringing us closer to a Landsat moment. On the other hand, if you talk to the end users and look at these surveys, it looks like the community is still interested in data sets like with faster repeat that have consistent global coverage, with finer resolution, and with greater vector diversity, so they could do three-dimensional deformation analyses. And also they would like these data sets to continue for many, many decades. So in a similar sense to how Landsat is being used for climate research nowadays, as it has a 30-year archive. I would like to add these, and I would say like these points were actually very similar to a previous talk by Paul Rosen at the USAR in 2018. I would like to add the frequency diversity and the full polarization to this list. So, you know, the more diversity that we have in terms of frequency and polarization, that will allow the radar community to do better in terms of classification and change detection. So then the questions that we still have to address and we are pondering still is how do we enable the above requirements in the near future? I don't think it's a capacity problem. With all the satellites up in the space, we likely have enough capacity to achieve these goals, but we need to be coordinated. So international coordination through bodies like ISPRS, IEEE is key to addressing these needs. In a sense, we also need to figure out how we are going to be able to leverage these small sets commercial constellations, whether they're public or private. And maybe one way of doing that is that we change our thinking in terms of how we define our science requirements. And instead of saying that we want the best data everywhere all the time, which is almost impossible to get, maybe we say we want the data everywhere all the time, even if it's not the best, but gets the job done. With that, I would like to thank you for your attention, and please feel free to ask any questions. And back to you, Lena.
Batu, that was great. Thank you very much. That was not only the coverage for all who are interested and experienced with remote sensing, SAR remote sensing, but also for those whom you just opened the window to, I guess. And I noticed there are more than 70 participants, so I guess there will be both groups. And I would like to encourage them to write questions in the chat, and I suppose you are ready to answer. Yeah. And it's up to you, but maybe I will read the first one, and sure. You continue. What algorithms do you use for ships detection? Is that neural networks or classic methods?
It was actually a classic method that we applied. So one of the advantages of synthetic aperture radar data is that it is very easy to separate water from objects. And especially if you're looking at the cross-polarization imagery, that tends to work better in terms of reducing the surface wave returns. So in most cases, we are using classical algorithms, meaning adaptive thresholding, with some smart backend post-processing, like fuzzy logic-based inclusions and exclusion masks, but no machine learning. Though we have a couple of our people working on machine learning algorithms on these things as well, but so far we didn't feel the need to.
Thank you. I will not read names of authors of these questions. So what about P-band biomass satellite? And given NASA was flying multi-band radar in the 1980s on the aircraft, the radar community has a long ways to go for multi-band, more than 3 bands satellite coverage.
Yes, of course. Yeah, P-band is definitely a key interest of mine. So I worked on actually a P-band airborne instrument when I first started at Goddard. And of course, UAV SAR has a P-band counterpart as well. And, we're well aware and eagerly waiting for the P-band biomass mission. The only reason I didn't include it was that it was a single case. And of course, the issues with the P-band, I'm sure the person asking the question is well aware, is the frequency allocation for global data acquisitions. So because of the missile defense radars, the object tracking radars that the defense systems have, the biomass mission will not be able to collect data over Europe, most of North America. So it will, of course, collect crucial data over high biomass areas, which is key for that mission and essentially why we need that observation. But I see growth in P-band in space a little limited due to this frequency allocation unless something changes. So with potentially other observations like airborne surveys and so on, I think those can increase. And I agree that the P-band would provide a better look at high biomass areas when we need it. So thanks.
Thank you. Another one, would it be possible to monitor coastal cliff collapses with open access SAR data, or the coexistence of water and steep vertical feature? The cliff in the same pixel is problematic?
Yes, so they have the right idea. It really all depends on the resolution of the data that you're looking at. So if the cliff collapse is large, and that is in proportion to the pixel size. So for Sentinel, roughly you could say 10 to 20 meters, right, resolution. So if the collapse area that you have is larger than that, then it might be detectable. And that's also very similar for the landslide applications that you're looking at, that we often have an issue with catching small scale landslides because of the resolution. But if you know the digital elevation model well, you might be able to do some modeling about how you expect the small scale changes to happen. But that is probably very tricky. And if before collapse you have deformation, you might be able to do that with INSAR, but in steep topographies, that also tends to be tricky because of the geometry. So you have to make sure the observation is seeing the face of the cliff and not from the back. So it is a challenging environment. So that is a good study area.
Thank you. I would like to encourage other participants to raise questions. And sure. In between, I would like to ask you, is NASA now analyzing the situation in the Canary Islands?
Oh, in the Canary Islands, yes. The disasters program has been activated for that. I am not actively engaged in it, but yes, there's a few of our team members looking at it to make sure that if there is a need for them to help in any way, that they'll be able to. But so one of the things with the disasters program, which I didn't highlight earlier, is that it really depends on a local end user's need. So if, very much like the International Disaster Charter, it has to be activated by a local organization. So, unless we know that people are asking for specific information, we will likely stay in monitoring phase.
Yeah, I think radar data and SAR equipment are a really powerful tool, which we still do not have enough energy and financing for to full use. And if you look at the instability in the world, especially in these volcano areas or fault areas and so on, we will, I suppose, maybe not we, but our kids will have a tool which will permanently measure the situation in the world for the pre-warning situations.
Yes, exactly. Yeah, I think it is. So it seems to me like that, we have the capability now. We know the technology. It's not a technical problem. We just have to get the resources in place to realize it. And often, especially with the government space agencies, the resources come after the interest. So it sometimes becomes a chicken and egg problem, because if you make it available, then people will start using it more. But on the other hand, in order to make it available, you have to show, our funding bodies that there is enough interest. So that is why I think education and training is key in expanding the user base for SAR data.
Yeah, I fully agree. I remember the situation with the first big flood in 90s of the 20th my country. And it was the company started to work on the data and then submitted that to the Ministry of Environment and so on and so on. So yeah. Another question. Thanks for the very nice talk. How will the NISAR data be accessible? Earth Explorer, can there be at least some low frequency application acquisitions?
Yeah. Yeah, thank you for the question. So I think NISAR data will be available through the Alaska Satellite Facility at the ASF. That is one of our NASA's data archive centers. And so it will be just like any other data sets in the ASF archive. As you know, Sentinel-1 is mirrored at ASF for now. And NISAR will be available similarly. There are actually some NISAR-like data sets over there. So what that means is that there are some UAV SAR L-band data formatted in NISAR data format, and also some Sentinel-1 data formatted in higher level NISAR data products, so that you could basically start looking at algorithms and so on with the same data formats. So it will be through ASF.
Are the P and L bands less suitable to coherence applied to agriculture?
Yeah, so I think it depends on the polarization you use. If you have cross polarization, they are actually perfectly adequate to look at agriculture. Since the cross polarization is much more interactive with the vertical structure. But if you only have a single band copolarization observation, you will get more return from the ground response and not the vegetation.
Will there be S and L bands in places other than India? Will there be offshore acquisitions?
Yeah, so there are, outside India, there are some calibration and validation sites that are already identified that will be collecting joint LNS mode data. And also in the coastal zones of India, there are S-band acquisitions over water too, but mostly NISAR's data will be collected over land.
Do you see the future of SAR data processing programs in cloud or still on local machines?
Yeah, that's a good question. Actually, that was one of the references I mentioned in the talk, that we looked at that, and at least we think that the growing volume and the desire to process large data stacks for the analysis will mean that it will be impractical to download all the data and do the analysis locally. So we are thinking more and more that the cloud processing capabilities will need to advance to make people comfortable processing online. But we're thinking that we'll likely have to come up with a cloud processing solution, especially for systems like NISAR. But you will always be able to download the data and process it yourself. That's I don't want to scare people off that find cloud confusing. So you could always download the data and do your analysis on your own.
I couldn't see any other question. Time seems to be going to the end. And
Yeah.
I would like to thank you so much for the effort you invested to the presentation and for all your scientific life you invested to SAR, because it's quite a long time already when you started to work with. And it's my pleasure to thank you on behalf of ISPRS, on behalf of ISPRS Council, and me personally. So best regards to all of you, and thank you for attention. And I hope to see, if not all, so nearly all next year in Nice, to be again in person contact with all of you and to enjoy the future better life than we have now. So best regards from Lena.
Thank you so much, Lena. Thanks for the opportunity.